high storage overheads. So yeah, the basic idea of a smart contract on one chain tracking the block headers and verifying the consensus of another chain. We have the main issue. You have basically two high overheads for storage. And in the current implementations, you have much greater trust assumptions than on the chain itself. So obviously there's a centralization risk, and these schemes are just not particularly secure at the moment, for as we've seen. So I think this is the most recent statistics I could find. So this is since September 2020. And yeah, so you can see 5 of the 6 largest exploits have been on bridges. So I think at least, I think the top 3 of these were all attacking multi-sig schemes. I'm not sure about the rest, but yeah, basically we need to remove this this centralization and the trust assumptions of using trusted bridging. So the basic idea is, what if we can just prove the consensus of chain 1 on chain 2 using a snark, and then we can use a smart contract on chain 2 that just verifies the proof. So in the zkBridge paper, they use a recursive proof to keep the gas costs and on-chain storage low. And there's a lot of things we could optimize, I think, and this specific aspect. So this would give us obviously a trustless and permissionless bridge. So nodes can freely join the network and then participate in generating proofs or relaying block headers. So the challenges to this are that in a proof of stake system, generating the proof for the large number of signatures leads to very, very large circuits. And we need to verify, so within the circuit, we need to verify the set amount of validated signatures, depending on whichever chain we're looking at. And we also need to verify that the signatures are from a valid committee or a valid subset of the valid data set. So this leads to very large circuits, and it makes the proof sizes very big as well. So in the zkBridge paper, they implement sort of a general structure that can be used not just for asset transfers, but they don't show us an implementation, but it can be used for general cross-chain messaging. So the basic idea is a sort of a lock and a burn and mint structure. So you lock tokens on chain 1. The headers will accumulate. So headers are batched, and I'll get to that later. But we can determine the number of headers to batch, and there's a trade-off then with the confirmation latency. But those headers are then relayed by the relay network. So this bit in gray is what the zkBridge network would consist of. So we have relayers who are relaying these headers to chain 2, along with proofs. So the relayer needs to generate a proof that the header that they relayed would be accepted by a like client of chain 1. So yeah, so it satisfies the condition. And then on chain 2, the minting contract can call the update contract, and once it's verified that those funds have been locked on chain 1, then obviously you can mint the tokens onto chain 2. So the main innovation here is basically this, the generation of the proofs and how efficiently that can be done. So in the zkBridge paper, they take Virgo as their sort of starting block, as their starting block proof system, and even though it's a very efficient scheme, if you have a large number of signatures, you just get huge circuits, so it still wouldn't be efficient enough. I'll just skip forward for 1 second just to show. So in blue is a sort of non-optimized, for this case, Virgo, and you can see, for example, if we have some consensus mechanism where we need 128 signatures, the prover time just is way too high. So they get around this by essentially distributing the proof generation, because you can think of the circuit for verifying each signature. So if we need to verify n signatures, we can think of it as n sub-circuits. So that can be then parallelized, and this allows us to scale up. So with linear scalability. So just to show, if we see with the green here, if we distribute that proof generation to 128 machines, you get proof generation time, I think, 13 seconds or so in their implementation. So their implementation is going from Cosmos to Ethereum, and it's practical. So the proof generation's not having much latency at all. So the problem with this is the proof sizes are quite large. So Virgo proof sizes are quite large anyway, because it doesn't have trusted setup, and this scales quite badly as well. So obviously it'd be too expensive to store on chain. So they use a two-step process where the distributed scheme gets the prover time to be practical for a large number of signatures. So yeah, 30 times speed up. It decreases the confirmation latency. So in this implementation, I think the confirmation latency is around 2 minutes, compared to some hours, for example, for optimistic bridges. So in order to lower the gas costs, the idea, just take the Virgo proof and wrap it in a Groth16 proof, and then obviously we have constant proof size and a constant gas fee. So another way that they reduce the cost for the prover is by, as I mentioned, the batching block headers. So this variable we could change, but there's a trade-off then between confirmation latency and the cost of proof generation. So in general, if we want to lower this, the costs are going to increase. So there's still some problems that they don't address in the paper, specifically relating to how the network itself will operate. So some things I think we could think about and discuss is they leave the incentivization of the relayers and proof generation. So yeah, those two roles could technically be separated as well and optimized separately. But there's no discussion of the incentivization there. We also need to consider in their scheme the way that they implement the distributed proof. You need to have basically a coordinator because they're basically running distributed sum checks, and we need to consider how best to coordinate all these different proof generators, and also then consider what might be the effects, for example, if you had a malicious coordinator. So I haven't really thought about the incentives there, because obviously it would be very expensive if you were going to break the protocol here. But for example, we need to consider if for example there would be slashing conditions for relayers who are offline, for example, or yeah, if you had a master node who was just breaking protocol. And then the last thing to consider is there a scheme or an approach which would be faster or cheaper to generate proofs? So they mentioned, for example, in the appendix, some approaches are that we don't necessarily have to generate the proofs per header. So we can, in fact, yeah, if it wasn't necessary for a particular block, then you wouldn't even need to generate the proofs. So in fact, you could just generate the proofs on demand. In that case, we would have to set up some sort of market for basically generating the proofs and then rewarding people for that. And then another area I think that there could be some optimization is in the communication overhead for the distributed proof generation. So the reason they've chosen Virgo as their sort of base proof, because as the base proof system, because it works well when you have these very large circuits, but there may be a possibility to optimize, I think, in this area here. Okay, so if anyone else has had a look at the paper and have any questions or any comments or thoughts about, especially these open problems.
Do you know if the proofs are actually being like computed by the network as such, and not just like as cores on a GPU?
Yeah, well, I mean, in the implementation they use, they have one implementation is Cosmos to Ethereum, as I mentioned, and yeah, I think all of their benchmarks are coming from assuming, yeah, it's just like a data center setup. But
yeah,
for
because
example,
that would change the like network costs quite drastically, I would imagine.
Yeah, they do. They actually price up if you were like the hardware cost for setting it up. If you were going to set up a node, for example. So yeah, like the cost per block are pretty like negligible, basically. But there's no. I mean, this is a whole thing. Yeah, there's no mention in the paper of how the incentivization will work.
Yeah, I guess it's more of like a specification than like a specific I mean, it has an academic flavor to it, right? Like it's not talking about a specific, game theoretically optimal protocol in that sense.
Yeah, and for example, with this malicious coordinator, yeah, like I said, I haven't thought about too much. I'm not sure what effect it would have on the proof generation if you did have a node, if the master node was just like not, for example, forwarding the messages correctly, or yeah, what effect that would have.
Well, presumably you could do liveness attacks, right? And you could hold users hostage and, say, if you don't bribe me 10K, I'm gonna, never let you bridge your assets either to that chain or back. You could do that sort of thing.
Yeah, I think Aaron mentioned this kind of attack, right? Or this kind of non-atomicity property.
Where does the cost per block come from?
So that is based on I think it was their AWS setup. Let me just get the paper. Yeah, so here in this part they're talking about, yeah, in the data center setup, and then in the appendix they have a similar setup with a single node, so the hardware needed. Yeah, I think it's here. I don't know if you can see that. So that was on Cosmos with 32 machines, because you'd need to verify.
Yeah. So a C524X large is $3 per hour, which translates to $2,000 per month. And that has 92 CPUs and 200 gigabytes of memory. I'm not sure, there are two questionable things here. Why we are able to rent such a high-end machine at only $250 per month from this other vendor? And if they can't, just based on the C524X large, that at 32 machines, that seems to be a lot of cost per month. And how exactly it goes to 0.02 per block? Like how many blocks did they divide it to? And are these?
Yeah, that's true actually, because it will depend on the batching as well. And I think they were batching. I want to say, I think they're batching 3 blocks.
Well, I feel this issue can be solved because this is a bridge. This is an application that can actually provide revenue. So what you can do is that you need to send a sufficient amount of the token so that the from 1%, 2% fee I charge is enough to cover my costs. And that's why I think Pro on demand will be useful here. If no one is going to send more than 1,000 USDT, then I just don't do those proof. And that will actually kind of make the model work a little bit better. I think you can think about this is that if zkBridge have additional benefit, then the bridge, and I think is that the bridge business already earn money that is far more than the cost they need to actually run the bridge. That is a liquidity business.
Yeah, but there are two issues there. One, the cost of running machines that can scale on demand, that's costing a lot more than a reserved instance or the physical instances that you otherwise set up by yourself. And in the AWS case, it's the difference between, say, $3,000 per machine versus if you buy your own machine with 92 vCPUs and 200 gigabytes of memories, and that's probably a lot cheaper than $3,000 per month. And the other issue is it's also not that feasible to just instantly fire up a bunch of instances when there is actually some demand. And rebooting or scaling those templated instances, it will cost time, a lot of time. Even in the GCP case, which does scaling better than AWS, it usually takes at least 10 minutes to do some simple, like say 2 to 5 or 2 to 10, that kind of level of scaling. So a user wouldn't be patient enough to wait for a scaling to kick in when there is actually a need. So that can be a that can be an experience problem. And also, how does this compete in terms of cost with other options, let's say centralized bridge operators with some kind of insurance premium? Here, if 1% of fees are charged to the users just for the operating the bridge, it doesn't seem to be competitive compared to a centralized operator and offering an insurance at 0.5% of the fees.
I got what you mean. I would say this is that for the cloud one, they do need to, I think is that if someone want to deploy this like design, they probably do need to have a contract with, probably doesn't need to be AWS and GCP. There are a lot of the cloud center or like miner, they have machine that might be able to do that. And and I would say I'm a little bit hopeful for that because this paper actually was implemented purely on CPU. Like when we are doing proof generation, we see a lot of the good result in GPU and other hardware, but this one never actually even used that. So I would actually be hopeful on that aspect. But I agree with you that this scaling that suddenly to a lot of the machine is not that feasible. Unless you do have a cloud like partner.
Yeah, it's a good point. Also, like, well, how do we incentivize other participants to join this mechanism? Given there's so much uncertainty in terms of how many machines are needed, what kind of machine is needed, and what level of resources need to be committed by the operator. It's not like you can say give them a grant, $100,000, and hopefully and let them take their own revenues. And it's not that easy for them to figure out how much money they can actually get back by operating this machine. And it seems having this kind of model to operate without censorship, like what James mentioned, requires at least like 2-3 participants.
My feeling is that so basically that I think whether or not this machine is run by a centralized party type is not that severe problem because it can only prove the consensus of another chain. And the MEB problem in this case will actually be smaller because what it can do is to synchronize exactly the state of the other chain. So maybe you don't, basically that you can have a distributed proof generation network for that, but it might not be necessary. And I think the main question is that we don't have that yet. But I think one point here is that we need to know the cause of this system.
So is there a potential attack vector which is, say I send my say some asset to the smart contract on chain 1, it gets locked, but the centralized bridge operator is down, and my funds are now just permanently locked in the smart contract on chain 1 with no possibility of getting them out? Or is that not
the operator can come back, right, in this assumption?
Well, they could, but maybe they're malicious and don't want to.
Yeah, it's kind of by the paper is it shouldn't be allowed for operator to do anything. They shouldn't be allowed to release or remove users' funds.
Yeah, what I'm saying is this is a potential problem with having a centralized bridge operator. Like, it's completely true, of course, that when we're dealing with zero knowledge proofs, the decentralization aspects, which we generally want in like censorship resistant networks, are, well, it's less important in some ways, but there are liveness issues which we should also think about and not take for granted that they're instantly solvable.
I feel that usually what they would do is probably to just have still like cloud partner. For example, if Binance want to run that, Binance can run one. Binance have several data center. They can have each one provide some backup, and they probably will sign a contract with this like big API provider that also have good machine, like for example Anchor. So, but I would say that clearly increase the cost even more. But that would be actually, I think, quite reliable backup solution.
I mean, I don't disagree with you, but the thing is, we're generally thinking about like worst case scenarios, right? Like, we want to, you know, as the cliches go, like trust code instead of people, and something like that would, in that sense, still not be enough, because even if Binance had signed those contracts, who's to say that they're not going to collude, you know, in a multi-sig attack sort of way? So I mean, it might be sufficient, but it might also not be.
So yeah, can I just add a couple of thoughts there? You guys hear me? Yep. Okay.
Yes,
So yeah, so a couple of things there. The first thing is as far as like if there's latency in actually bridging those funds and sort of minting them on the other side, you can always put in a mechanism in place where you have a confirmation back that these funds have been minted, and then you could have some sort of mechanism where if these haven't been minted on the other side in a certain period of time, then you can give the user the ability to unlock those funds, right? So it's not like they'd have to be stuck there forever.
That would require communication from the destination chain back to the source chain. It adds
Yeah,
another.
you need the other layer for the confirmation.
You can't even do it one side. If one side is already one way is already blocked, how do you expect two ways will not get blocked?
Well, the point is that if it's blocked, you just have a timeout mechanism that if you haven't received a confirmation that has been minted on the other side within a certain period of time, then those funds are now able to be unlocked.
But how can the smart contract on chain 1 know that I have received or haven't received the confirmation on chain 2?
You'd have to send the confirmation back the other way.
Yeah, it
So
also
you double
introduces
the
another advantage. So have one-way confirmation, and then block. So first you need to transmit from source chain to destination information. Then you block the confirmation. And then the source chain believes all the funds are somehow not minted, therefore release back to the user. So
Okay.
that's
So
unless you make a three-way hand, like a TCP.
a three-way, yeah. That's a good point. The other thing I just wanted to say, and so I haven't got a solution with that. The other thing I'd say though is that any funds locked is an attack vector, right? Like once those funds are locked, some of the hacks have been not so much on the proof of the transactions going through, but basically those vaults being hacked, the keys for those vaults and attacking the funds that way. So the other thing is, if James, could you bring back up that slide, the last one where you had the open questions on there? And I'll just run through how some of these have been handled in sort of chain, like I'll use Harmony as an example because it's what I sort of work best with. So the incentivization of relays and proof generation. I think as was said earlier, as Wei King said, you could have like a token, or basically the relayers would actually get some sort of transaction fees or some sort of payment for generating those proofs, right? And typically with Harmony, you basically would select a subset of validators. In this case, there'd be proof generators, and they would be selected like per epoch. And then if you're selected, then you have the ability to generate those proofs, and there's economic incentives for that. As far as the coordination of relayers to optimize the network resources, once again, what they do with Harmony is basically the coordinator really just collects all the signatures, and then once they have all the signatures, they send them back out to the validators to validate the set of the signed block headers. So I'm not sure whether or not in this model the relay would coordinate the acceptance of the proofs and then send out those proofs to be like verified a second time. I'm just like, as far as that goes, what that does is it takes off like the ownership of the proofs from the coordinator and basically puts that, once they're coordinated, once they've got all the proofs, they send them out and other people validate that they've got the correct set of proofs. The other, as far as the management of offline relayers and malicious coordinators, what happens is if you don't have a response, like if you're a coordinator and you haven't like coordinated like the proofs within a certain period of time, you get unelected effectively, and you switch over to someone else who takes on that coordinator role, and then you obviously get slashed for that. And yeah, they're just the 3 points that I'd share from what I've seen in other implementations.
Right, it's possible, right? Because they're validators, so they're already staked, right? I mean,
right.
Yeah. So in this design, like, yeah, we need to consider that on top of it as well.
So one way is staking, but the other way is just basically the economic rewards being able to produce the proofs. And if those rewards are high enough, and then you have some sort of reputation system of these people have consistently like provided the proofs, and based on their reputation system, they're more likely to be given a slot to produce proofs again. That's another way of approaching it. But the question for that is like, how do you like new players sort of come in and sort of become eligible for that without like staking? So.
I also think with the faster proof generation, so one of the reasons that I think I mentioned this in the channel, like one of the reasons they choose to use Virgo is because it doesn't have trusted setup. But then we're using proof aggregation scheme anyway. I mean, we're using Gross 16 anyway. So it might be possible to speed this up somehow. But then I was thinking, I don't think that proof generation latency is really it doesn't have that much effect, because the greater effect is, for example, if you're batching, having to wait for a certain amount of headers. So yeah, whether we could optimize on confirmation latency through the proof generation itself, I'm not sure.
I mean, it could maybe use like something like snarkpack or aplonk, because isn't the idea that the proofs are generally, you have some block header, you prove the validity of the block header, then you prove that all of the transactions, all of the messages sent to the bridge are included in that block corresponding to the block header. And you can do those, for each of those transactions, you can prove that in parallel and then just aggregate it with like aplonk, right? I think that should work.
Yeah, theoretically.
Yeah. I don't know how efficient that would be relative to Virgo. I was also curious, you said something about recursive proofs. Where does the recursion come in?
So where it's just a simple where they take the Virgo proof and
Oh, and wrap it in growth
and
16.
wrap it in
Okay.
growth 16. Yeah.
Okay, I was wondering if there was
not multi-layered, just wrapped in
okay,
growth
so
16.
it's not like a Mina style thing where you're
No.
continuously like, okay, yeah.
But that's what I mean. On that area there, I think it's possible there could be a better way of doing that. But yeah, like I said, the problem is the circuits are just huge. Like, I can't remember, million
why are these circuits so large? They're doing something like 100 signature checks non-natively. Is that right?
yeah. So they're the one they implement, it was yeah, it's because they're doing all this non-native arithmetic basically, and on 128 signatures. So
did they say how they're doing the non-native arithmetic? Because there are a lot of different approaches to nowadays to speeding it up.
I'm not in any particular detail.
Okay.
Yeah, so you were mentioning that, I saw in the channel, right?
Yeah, it could be possible to altogether avoid non-native arithmetic if we just chose our field to be the base field of whatever the signature curve is. With zkP or ED 25519, it doesn't have the two-adicity that we need to do FFTs. But we could use snarks that don't require FFTs, or we could use like evaluation algorithms that don't require two-adicity.
So Virgo uses multilinear interpolation, so that's gonna be FFT free anyways, and it's O of n.
Oh yeah, so why don't they just choose the native field then? Well, isn't Virgo based on low degree test? So is there a low degree extension that like kind of hidden in there?
Yeah, they do multilinear interpolation to compute the multilinear low degree extension and then run some check on that, and I think some low degree tests as well.
Okay, so it sounds like there's a hidden FFT, but it could probably be instantiated with KZG or something else to avoid FFTs.
Yeah. I mean, then we're suddenly at Hyperplonk, right?
Yeah.
It would be interesting to see a look at. But is speeding up that proof generation a critical part of it? So yeah,
I guess also with the D Virgo, that is a proving scheme that there's no equivalent to in terms of other schemes that we know where you can just distribute the proving and not have too much overhead.
Yeah.
Is D Virgo that related to Virgo?
So yeah, so that's the distributed scheme that they're using.
So is Virgo actually essential in this whole thing? And can that be simply swapped out while we keep the distributed mechanism?
I mean, what they implement is specifically built around Virgo.
I mean, it's a modular design, right? So it doesn't really matter. But in this case, they've chosen Virgo, I believe, because they need to distribute the proving somehow anyways, because they need to break up the circuit since it would otherwise be too big. And they came to the conclusion that Virgo was the best for doing that because you can do this distributed proving.
If we did use the native field, I think we could just make it fast enough that we don't even need recursion. It should probably take less than a minute to create a proof, to prove 100 signatures.
How does
So
that work
I
exactly?
think what
Do you have the freedom to do that?
To the freedom to choose the field, you mean?
Yeah.
I think so, right? Or yeah, why wouldn't we?
you have to use non-native like computation and like somewhere because at least one side is BM curve, the other side probably signature. Usually is not BM curve. So what they do in that paper is actually have Virgo to do the like non-native part, but Virgo will be using the field of BM254. So a gross 16 proof can be generated like by to verify the Virgo's like proof.
Oh, but why would we do both in one circuit? I thought there would be one circuit for one side and one circuit for the other side.
Well, you mean that like one circuit on the center side, one circuit in the receiver side, or?
Yeah, I thought we would have one checking Ethereum consensus for, say, Cosmos, and then one checking Cosmos consensus.
Yes, and I think they will be different because these two chains will have different consensus, especially Ethereum now 2.0 with BLS signature, right?
Mm-hmm.
Although natively we cannot verify BLS 12.381 easily.
Mm-hmm.
Wouldn't there also be an issue here when using two different schemes? Then we would have to do the proof verification in non-native arithmetic, and that would be far from ideal, right?
An ideal way is for Ethereum to kind of have the 1962, basically making like EVM support, like have all the curve, kind of like that. But at this moment, it's just the BM curve. And I think soon, which means that at least 1 year later, they will have the support BLS 1231 curve. But neither of these will solve the problem of like basically non-native computation because what I need is not a curve that is the signature curve. What I need is a curve that can efficiently verify things on BLS 12 or BM curve. But this also leads to one of the other solutions because zkBridge is not necessary if you can just provide the signature to the smart contract directly and have the smart contract to verify that. That is also a like alternative. Basically, if your chain is like flexible enough that the chain can support just directly verify the signature and the signature is not a lot, then there is also a version of the zkBridge where just to have like layer one verify the signature directly. But basically there is a lot of this thing that the chain can change in order to kind of adapt to like bridging in general. And maybe you can remove even the needs of the zkBridge. Thing about this is basically like an oracle. Maybe it's just all the nodes in your network also is known in other network so that they know the state of that. And there's a pre-compiled contract to ask them to get what they think is the state. But we basically, that is very difficult to assume that one of the chain will do the upgrade that actually will be suitable for zkBridge. So zkBridge kind of have to adapt to this existing chain.
Just to clarify, so about the non-native arithmetic, are you saying we still need recursion because let's say we pick a field that lets us verify Solana signatures cheaply, but then we still need to get that to check that proof in the EVM, and the EVM only supports BN arithmetic, so we would still need a BN based wrapper.
Yeah.
Right.
Well, in that case, you probably would just not use like this like curve because that non-native pairing is very terrible. So we generally avoid that. And I think it's mostly related to this, that EVM could do all the curve. There's nothing special with BM curve, BLS curve. It's just that EVM have the pre-compiled contract for one thing, but not the other. And this is a limit that is actually EVM's problem. But like I would say, it's just not easy to change now.
So I think what we could do, we could pick a field that's optimized for verifying, say, Solana signatures and generate a Fry-based proof to check Solana consensus. And then in that Fry-based proof, our hash output would be the BN scalar field. And then we would wrap that in Groth16 BN proof, where in this recursive circuit, the hashing would be native because we hashed to the BN field. This is what we do with our zk EVM.
I think it's more about that we need to check the cost of this. There are two parts of the overhead that we need to be careful for. First of all, we know that if there is a lot of signature, then this will win because you are reducing the cost of signature verification. This might also reduce like the cloud bills. But there is also, remember that because using gross 16 to kind of compress the proof, we also introduce latency. And that one, if not controlled very well, it will be longer than a block time. And so basically this system have a limitation is that it can also have a part that is for the gross 16. And this part, if we make that circuit too complicated, we may already miss like the block generation like come.
Yeah, true. Yeah. I think it takes around a minute in our current prototypes.
I noticed in the paper it never discussed a few things. One is the necessity of Virgo and why it was chosen, and how it's related, and how deep Virgo is related to that. And the other is when it comes to generating the proofs, the time spent on each part, relating to the discussion between Wing Kang and Daniel just had.
Well, kind of they are also at Berkeley, but basically I would say this is an academic paper. So what they can do is basically to test on one chain, one situation. And they didn't, well, we don't imagine that UC Berkeley like team will actually do all the bridges and give us a very comprehensive like discussion of all that case. So I would say that like there are just a lot of number that we need to figure out. The Virgo is actually already open source. If you try the Virgo repos, but like other branches, you might be able to find the code of that. One of the reasons why people choose Virgo is that like, so there is a reason that Virgo or all these like GKR protocol could be more efficient than other protocol. And I think this will be a very interesting point for like Daniel. Basically is that in GKR protocol, you only do polynomial commitment on the input. And for other protocol, we do polynomial commitment, not just on the input, but also on the computation logic. And like basically GKR have the like benefit that if the computation is highly repeating, basically just a repetition, then you can get a sublinear time verifier. So in this like specific case, you might actually have a proof system in which you only do like polynomial commitment for the input, but not anything else. And for the rest, it will just be like a bunch of this like GKR like protocol, opening like multilinear extension. Virgo's main problem is that if the circuit doesn't have structure, then it have a linear time verifier. That's not going to be useful for like smart contract. But if that is highly repeating, then the cost is basically one computation plus log of the number of repetition. So basically that he is very suitable for repeated computation. And I think they didn't discuss that. The point that like basically Virgo is only useful when the circuit is what they call like lost space like circuit. This is not like generally discussed very often.
Yeah. Given that the actual repetition is reduced from 128 to 32, it is and generally for other tests, it doesn't require a high number of validator signature verification anyway. Whether it's necessary, it remains to be seen. We need
I
numbers.
think this also touch one question that is now actually zk rollup, zkBridge, and all these like zk project that actually need to verify approve in the layer one. That's the gas cost. It seems that the best number I see is also from Polygon, 230,000 like for gross 16, but we just want to know whether there is any way to do it better, even for some specific application.
Did you see the FF Planck work? I think they got it under 200K with that technique.
I didn't know that number, but okay, that is pretty good news.
I think Zach said 180K.
Will we be able to get something that 20K or 30K? I'm just thinking.
Mm-hmm.
Yeah, maybe we should we should wrap up here. We are severely over time. I was asked if I want to talk about the Horizon paper, but I think it's probably best to leave it for the next time. And it's also a different flavor. It's very practical.
I
Doesn't
have the
have
feeling that this meeting now is usually 1 hour, and we usually only discuss the first paper. Is that true?
Hmm.
I agree with this.